Mm-hmm. Not that I know of. That's been there for months.
Now there's some pen and paper.
Awesome. Okay. So do you guys remember when we did hypothesis testing before? Okay, we're looking at the snow?
It's so pretty.
It's so pretty. It's a pretty focus. Okay, you can focus and you can go outside and play in the snow when you're done with your quiz, right? Later, not yet. So in chapter 4, we did hypothesis testing with those two-way tables and chi-squared tests. Does that ring a bell? We're going to do this in a more general sense. We're going to review some of the hypothesis testing stuff in today's lesson. And we actually won't begin doing hypothesis tests until Wednesday. They're going to be a little bit similar to confidence intervals. We're still going to use z-values and t-values. We use z-values with what things? Proportions. And you use t-values with means. Okay? So it's that same parallel also holds for the the testing stuff. All right. So this was a quote from your textbook, and I thought it was pretty cool. So the logic of statistical hypothesis testing is similar to the presumed innocent until proven guilty principle of the U.S. judicial system. So we assume that the null hypothesis is a possible truth until the sample data conclusively demonstrate otherwise. Okay, so here's the kind of the principle. You assume, what was the symbol for null hypothesis? Do you remember? So you assume H0 is true. You do some calculations. That show something. The one thing that they might show, H0 is, say, super unlikely. Given your data. That's kind of like the presumed innocent until proven guilty thing, right? Like, we assume you're innocent, but then we found your DNA and we found other stuff at the crime scene, which makes it seem very unlikely that this is actually a truth, right? It's the same kind of idea. You assume this null hypothesis is true. You take your data and you figure out how likely is this data given that the null hypothesis is true, and either it's possible or it's super unlikely and you say this just can't happen, it's probably not the case, therefore we accept HA. That's the principle. You have this hypothesis that you're trying to knock down. That's a common thing in science, isn't it? Yeah. You have a hypothesis, you have to disprove it. Okay. So the first thing are, how do these hypothesis statements work? So the blank, represented by the symbol blank, is a statement that there is nothing happening. So nothing, null. This is the null hypothesis. So it's represented by the symbol, you already said, it was H0, H sub 0. And look, you even say it right, H0. Yeah, but we just read H0, right? Right. Is a statement that there is nothing happening. So the specific null hypothesis varies from problem to problem, but it can generally be thought of as excuse my, don't know how spell check didn't catch that one, the status quo, or no relationship, or no difference. In most situations, the researcher hopes to disprove or reject. Okay, I want to know the first one was null hypothesis. What is the other hypothesis? Alternative hypothesis? And what's the symbol for that? H sub A is a statement that something is happening. In most situations, this hypothesis is what the researcher hopes to prove. It may be a statement that the status quo is false, that there is a relationship, or that there is some kind of difference. So let's practice writing these things both in words and in symbols for specific situations. So I want to make sure that you can do both. Okay, so first thing, suppose that a pharmaceutical company wants to be able to claim that for its newest medication, the percentage of patients who experience side effects is less than 20%. So the thing that they want to prove, that's your HA. State null and alternative hypotheses in words using mathematical symbols. Okay, so H0, HA. So HA is what they want to prove, and what do they want to prove?
that newest medication has less than 20% side effects?
So we're talking about a proportion or a mean here? Proportion. So the proportion who experience side effects when taking this drug is what? Less than 20%? So that's in words. Mathematical symbols is nice and short. But you've got to use the right symbols. We're talking about a proportion, so we're going to use P. Does that make sense? So P is less than 0.2. And H naught would be that the proportion who experience side effects is what?
It's greater than 20%.
Or 20% exactly, right? So 20% or more. So that'd be P is bigger than or equal to 0.2. The H naught always gets the equal to.
Proportion who do not experience side effects.
Portion who, yes. Thank you. Wait. The portion who no, it's due. They're talking about this, they're both due, but it's just the amount of people who do is different. Does that make sense? Yeah, so they're both due. Just that in one case it's less than a certain value, in one case it's bigger than or equal to a certain value. And I think I said this, but I'll say it one more time. The H naught always gets the or equal to. Okay. This one did specify a direction. Do you also understand that in the directions? Mm-hmm. That it said something I wanted to presume was less than a specific value? The next one doesn't specify a direction. There is a distinction we'll have for stuff like this. A researcher wonders whether men and women have different average body temperatures. Probably the case. But anyhow, let mu1 be the mean temperature for all men and mu2 be the mean temperature for all women. State the null and alternative hypotheses. So in this one, what is nothing going on? Nothing going on would be that they have the same. Yep. So men and women have the same average body temperatures. What is that in symbols?
mu1 equals mu2.
Okay, that's the first way we're going to write it. We have information for differences of means, don't we? This statement is often rephrased as mu1 minus mu2 equals 0. Do you buy that those are the equivalent? Okay, so this is definitely the more common way to write that. So for stuff that talk about differences either for proportions or for means, express it as related to 0. And HA is that men and women have different. Did they specify a direction? No. And since they don't specify a direction, then you just say mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0. Okay, is that all right? Okay, and what this is saying when they don't specify a direction is that that relationship could go either way. It could either that men have a higher temperature or women have a higher temperature. Either one is possible, whereas the previous one, they really care about the direction. Now, that kind of difference where you have some sort of direction specified or no direction specified is the next thing we're going to talk about. And when you have one direction specified, this is called a one-sided hypothesis test. And this is what happens when the alternative hypothesis specifies the parameter values must go a specific direction from the null value. So your proportion who experience side effects is less than something. And we're going to, this will change our p-value stuff a teensy bit. So just, you know, distinguish if stuff is one-sided or two-sided. So one-sided means you specified a direction. And a two-sided thing is when the alternative hypothesis, it could go in either direction. And this is sometimes called a two-tailed hypothesis test. What the tails refer to is that when you have this bell curve, looking for the chances that you land in a specific tail, either a lower tail or an upper tail. That depends on which way your inequality went in the original statement. But for a two-tailed test, what do you think that means? You could land either in the lower extreme or the upper extreme values. If you think about probabilities as area under curves, like you see how this would be like, say, twice the area of that guy if they were at the same value. Okay. So that's the one-tailed, two-tailed distinction. Okay. So I'm going to give you some hypotheses. You've got to tell me, are they a null or are they an alternative? And let's just write down what they are. So the average weight of Canadian geese is the same as Canadian warblers. So let's let, I don't know, mu g equal the average goose weight. And mu sub w be the average warbler weight. I have no idea what a warbler is. Or are they at all? I'm not a bird person. So what is this saying? The average weight of geese, Canadian geese, is the same as the average weight of warblers. It's either saying mu g minus mu w equals 0 or that those two things are equal, right? Is that a null or alternative? That's a null, because null is nothing going on, same. Mu g minus mu w equals 0. So this is a null hypothesis. If you say the word null or put the symbol H naught, both things are fine. Okay, either one's okay. Would the test be one-sided or two-sided? Did they specify a direction? No, so then it's two-sided. So two-sided, no direction specified. Okay, is that all right? This one. The proportion of books in the local public library that are novels is higher than the proportion of books that... Wait, what?
Yeah, it looks like it says the same thing, but it's public library and university library.
Oh, yeah. Oh, yeah. Thank you. So let's let P1 equal the proportion of books that are novels in the public library. And let's let P2 be the proportion of books that are novels in the university library. Okay, so what is this saying in words? The proportion of books in the local library that are novels is higher than, so this is saying P1 is bigger than P2, isn't it? Mm-hmm. Yeah. Or it's saying that P1 minus P2 is bigger than 0, right? Since that doesn't include an equal to, it's alternative, exactly. So that's HA. Does it seem like a reasonable assumption? Public libraries have a higher proportion of novels than university libraries? Probably they have more fiction at public libraries proportionally than universities. Like the university library here has like some of the math textbooks I use as a graduate student, like stocked. And those books probably don't exist at public libraries. Like nobody wants to read about topology in the real world. Probably not. Okay, this was a one-sided test. Yes, thank you for asking. And that was because the direction was specified as being higher in one way. Yes?
When we get, like test questions wrong, can we write one tail and two tail? Do you care?
You can write that too. But mostly this is just to introduce the idea so that when you have to do a test, you can distinguish which one you're doing. So it probably won't be a test question that's just like this, but you'll have to use it to do a test question. But one-tailed, two-tailed, same thing. Okay. The average price of wool jackets in New York City is lower than the summer than the winter. Okay, so like mu1 is the average price in summer of a jacket. Mu2 is the average price in winter. So what has this stated in those symbols? Mu1 is lower than mu2, right? Or mu1 minus mu2 is less than 0. Look at that. Okay, yes, I know I added stuff. Now go away. Okay. Okay, because they said lower, not lower than or equal to, this is alternative again. Yep. And because they specified a direction, this is also one-sided. Okay. The proportion of students who receive A grades from Professor Harrington is the same or higher than the proportion who receive grades of A from Professor Cantor. So let's let P1 equal the proportion who get A's from Professor H. And P2 is the Gesundheit, proportion who get A's from Professor C.
Would it be P1 is greater than or equal to P2?
Mm-hmm. And the fact that the or equal to is there means that it's officially H naught. So this is the null hypothesis. And is it one directional or two? It's still one directional. Or what did I say? One-sided is what I said. Yeah, same thing. Okay, so the test statistic, the p-value, and deciding between these two hypotheses. So the test statistic for a hypothesis test is the data summary used to evaluate the null and alternative hypotheses. So back when we did chapter 4, our test statistic was this chi-square thing. Remember that? And when the chi-squared was big enough, you got to reject your null hypothesis. Does that ring a bell? And that chi-squared being really big meant what about the p-value? That was really small, okay? For stuff like this, we're doing a little bit different things. We're going to have z statistics and t statistics. They won't be chi-squared stuff, but it's the same basic principle. If your z value you get is large, that's evidence to reject the null hypothesis because of the low p-value.
And there's going to be like a set value?
There'll be like a set value, exactly. Yep. There'll be a set value for your z value that corresponds to a specific probability, a p-value. You'll use that table that you have to find p-values. You'll get out a specific z, and then you find the p-value for it. Okay. So
Using the Z table.
we'll be using the Z table, but we won't bring it out again until Wednesday. So the p-value is computed by assuming that the null hypothesis is true, and then figuring out the probability of a test statistic in the direction of the alternative hypothesis under that assumption. Like, if this is true, how likely is it this would have happened? That's kind of what's going on here. So, like, for example, so we have a study, and surgery patients either started taking painkillers before the surgery or didn't do so until they woke up afterward. And the hypothesis was that it just doesn't matter when you start taking painkillers. But among the pre-surgery painkiller group, only 20% still had pain 9.5 weeks later. And in the other group, 60% still experienced pain after 9.5 weeks. It's a pretty big difference, right? And so the p-value was reported as 1 in 500. So 1 in 500 as a decimal is 0.02002, right? So what this means is that a difference this large is only going to happen with that probability if the null hypothesis of no difference was true. So let's write it down slowly. So a difference this large occurs with spelling. Probability p equals 0.02. If we assume H naught, or there is no difference in the two groups is true. So what you assume that, okay, taking painkillers doesn't matter when you take them. You take them before, you take them after, it's not going to make a difference. And you assume that. And you say, well, I have this group of people, and I gave half of them painkillers before and half of them painkillers after, and here is the differences in pain of 9.5 weeks. If there really was no difference, I'm only going to see this due to chance 0.2% of the time, which is pretty unlikely, right? That's not very likely to happen. Do you agree with that? And so since this is not very likely, you would say, yes, there probably is a difference. I should give painkillers before people have surgery. That's the principle. So probably would, in this case, because this is so unlikely, you would reject H naught and start giving painkillers before surgery. Do you remember what the p-value threshold was for last time when we did this? Because we had a specific p-value that I said when the 0.05, which is saying like a 5% chance. This is less than a 5% chance, right? The threshold that you set varies from situation to situation, but 0.05 or 5% is pretty common, okay? And that's the next thing we've got. So level of significance, which is denoted by the Greek letter alpha, just like a little fish. This is a value that is the borderline for when the p-value is small enough to choose HA. Like we had that 0.05 before, right? Once your smaller p-value is less than 0.05, you reject H naught and accept HA, right? Does that ring a bell? Okay. When the p-value is less than or equal to alpha, you reject the null hypothesis. When it's larger than alpha, you cannot reject the null hypothesis. And it's also a common practice to call a result statistically significant when the p-value is less than or equal to 0.05. A lot of you were confused by this last time. Saying something is statistically significant is the same thing as rejecting H naught. Those are synonymous. Okay, rejecting H naught and saying this result is statistically significant, the two things are equal. So when the p-value is small enough, we reject the null hypothesis or accept the alternative. So small enough is defined as p-value less than or equal to some alpha, and it's usually 0.05. And when the p-value is not small enough, you conclude that you cannot reject the null hypothesis. Not small enough is defined as p-value bigger than that alpha. This never means H naught is true. Kind of like not guilty doesn't mean innocent. Not, right, could be. So you could have failed to reject H naught because your sample size was too small, for example. Or it could have just been like a weird sample where you made a mistake. All right. So if my level of significance is 0.05 and my p-value came out to be 0.10, could you reject H naught or would you fail to reject H? And the question you ask yourself is your p less than or equal to 0.05, yes or no? So is 0.1 less than 0.05? No. So you fail to reject H naught. And the conclusion that could be made, there's really no conclusion. H naught might be true, might be not true, you just don't know. Bummer. Get a bigger sample. What if the p-value came out to be 0.01? Is this p less than or equal to 0.05?
Yes.
Yes. So in this case, you would reject H naught, right? And then accept HA. And occasionally your significance level can be set a bit lower. Like if I set my level of significance at 0.01, is this p-value smaller than it? So is p less than 0.01?
Yes.
Yes. So still reject H naught, accept HA. What time is it?
1:30.
Okay. I probably should stop there because you get quiz time. So let's stop there. We'll finish the rest next time. So when talking about hypothesis tests, you're usually trying to reject your null hypothesis and you don't really know if it's true or not. And there are different kinds of errors you can make. And so here are the two different kinds of errors. So a type 1, something called a type 1 error occurs when the null hypothesis is true. So what this means, so H naught is true, and the mistake that you make is that you reject it and accept HA. So suppose I had a null hypothesis that quizzing doesn't help test scores. And my HA was that quizzing does improve exam scores. And quizzing, like H naught was true, and then, but I was like, oh no, accept HA, and I'm going to give you quizzes, something like that, right? And a type 2 error occurs when the alternative hypothesis is actually true. So type 2 means HA is true, and the mistake is that you fail to reject H naught. Something I didn't realize with these names is that the type refers to which hypothesis is true. Do you see what I mean by that? When we list our hypotheses, we list H naught first and HA second, right? So hypothesis 1 is, which one?
No.
H naught, right? So hypoth number 1 is H naught, and so a type 1 error is when H naught is true. right? And hypothesis number 2 is HA. So the type 1 mistake is when H naught is true, but you mistakenly reject it. Does that make sense? So that's what those types refer to, which makes them a little bit less arbitrary as definitions. Yes?
A way that I've learned to remember it is type 1 errors are ones you usually actually see in articles. Type 2 errors usually end up in the trash bin because you don't end up seeing them because no one publishes stuff.
Yeah, that's a really good point. Yeah, so this is not published. Yeah, you're totally right. So say that one more time because it was really good.
Oh.
So the first thing,
Type 1 errors are usually the ones that you see in like actual like published articles, and then type 2 usually ends up in the trash bin.
yep. Because small p-values get big attention. And so there is actually a problem in research that, so there's this over-exaggerate, you see these extreme cases as the ones that are reported. And so yeah, these are the ones that you will see in articles that are not actually results. And these are just not published because you think nothing's going on when there's something is. Yep, that's a really, really good thing to point out. Thanks. Okay, so let's talk about what that error would look like in a specific case. And I'm sorry for the fact that it's politics because I'm also really tired of this. So there are 3 factors that affect the probability of making a type 2 error, as in throwing your stuff in the trash. This is where you would trash your research. The first thing is the sample size. So if your sample size is too small, that's going to increase this probability that you have a type 2 error. So bigger, better. The level of significance. If you make that alpha really, really small, it's really hard to reject H naught. So, keeping alpha at a reasonable level is something you got to do, which it's usually 0.05, but there are arguments for it to be other things. And then the last thing is the actual value of the population parameter. The farther that parameter is from the null value, the lower the probability of this type 2 error. That's one thing that makes election guessing really hard because the country's pretty close to 50-50. So having a group of people be 53% one way isn't that different than 50% one way. And so that's what makes election guessing, I think, tricky, as we saw. So here's the example. So we have some politician, I don't think they make decisions this way, but we'll pretend, is trying to decide whether to vote for a new tax bill that calls for substantial reforms. A random sample of voters in his district leads him to believe that HA, the proportion who support the bill, is bigger than 0.5. And as a consequence, this person decides to vote for this bill. So what would a type 1 error be in this situation? What would the consequences be? Okay, so type 1 error means H naught is true, right? And what would H naught have been in this case? If HA is that the proportion who support the bill is bigger than 50%, what is H naught? Is less than or equal to 50%. So P is less than or equal to 0.5 in reality. I think I just spelled reality wrong. Oh my God, don't judge me. In reality. Which means in words that in reality less than 50% of his district supports the bill. Does that make sense that that's the same thing as H not being true? Okay. And what he does, but he votes for the bill because why? Because he thinks that P is bigger than 0.5. Exactly. So what happens here is that he is supporting a bill that less than half of his voters supported. Like, that's the consequence, which might have ramifications for him. Yes? I mean, it just depends. Okay, does that make sense? Okay, let's talk about the type 2 error in the situation. So type 2 error means that then H of A is true, as in P is bigger than 0.5 or more than 50% of voters in this district support the bill. Okay, the mistake here is he fails to reject H naught. And if you, it doesn't necessarily mean H naught is, like, failing to reject H naught just means you don't have enough evidence to, like, conclude it's false. So he doesn't have enough evidence that support is over 50% to vote for this bill. So, does that make sense in terms of what the error is? So probably if this person failed to reject HJ, he would go with kind of just accept that H naught is true for now, and he would, like, not vote for the bill, right? He would not vote for change because he didn't think anybody wanted it. That would be the logical conclusion, right? Doesn't mean it's true, but you just, they operate under that's the assumption for now. What error do you think is worse? Do you think implementing change when it's not wanted, or not doing change when it's, well, I guess it depends on the situation, right? Because both of them are bad consequences, but people don't like change. Would you agree with that?
I think it just doesn't, I mean, it depends on the person.
Huh?
I don't know, like, when
I don't know.
Everybody voted for
Got a
change.
different opinion, moral compass.
So I think, I think this question really could go either way if you give me a good argument, okay? So, but since it said that this calls for substantial reforms, we're talking maybe about lots of change, and voting for lots of change when it's not necessarily wanted might be worse. Does that seem like plausible?
No.
Maybe? I mean, you could go either way, but I think that type 1 error,
Yeah.
voting for a bill that implements substantial change, when it's unwarranted, may be more damaging.
Could we say that, like, it has different types of factors that play into it?
Oh, yeah, definitely. I mean, like, just give me some logical sentence about why you think it's one or the other, and I think that it's not the case that one is necessarily right.
Exactly. So, for example, like substantial reforms, like what exactly would you consider?
It depends on, it would depend more upon what kind of substantial reforms those actually were and what situation they applied to. I totally agree that this really could go either way. Yep. Yep, I totally agree. Okay, and then the last thing on this little note sheet before I move on to actually doing hypothesis tests, So the power of a hypothesis test is the probability that we decide in favor of the alternative given a specific truth about the population. So what this means is that when HA is true, so we have HA true, the power is the probability that we don't make a type 2 error, as in we don't fail to reject, right? Because type 2 is the garbage research where HA is true, but you failed to establish that that was actually the case. So how do you, the best way, so here's one quick example before we move on. A researcher is deciding whether to use a sample of 100 or to increase sample size to 200. How will this affect the power of any hypothesis test?
Bigger sample size means more accurate result.
Yep, bigger sample size, more accurate result. So a bigger sample size reduces,
Chance of type 2 error.
reduces the probability of type 2 error. And that is more power. Oh my goodness. Did you guys watch Tool Time? This is like Tool Time. That was an old show, right? Ages ago. I mean, that was when I was like younger than you guys. More power. Okay, sorry. Stop with the stupid stuff. All right, so I think the thing we should actually do some hypothesis tests. You will need a z-table, so if you don't have one, grab one. If you do have one, get one out while I save this and pull up my next slide.